So last time we talked about how to represent any periodic function f of t that's periodic in t. So, f, your fundamental frequency is 1 over t, and therefore your fundamental frequency in radians per second is 2 pi over t. And we said if you've got this f of t that's periodic in t, you can represent it as a sum, as a DC component, plus the sum of different signs. And how much of these signs? Some amount a sub n. So it's a sub 1 times cosine of omega naught t plus a sub 2 cosine of 2 omega naught t, and so on. And then plus not only a cosine, but also a sine. And that's what we said last time. This is not a particularly intuitive thing, but it's easy to calculate these values of a sub n and b sub n. What's far more intuitive is to represent them as a sum of pure cosines that have some variable magnitude and some variable phase. And so this is the intuition. And if you want to calculate these values, we say that a sub naught, it's the same thing as capital A sub naught. It's the same thing as the DC value. It's the same thing as the average value. And in math language, it's equal to 1 over the time period times the integral over any time period of your function of t dt. And that's the formula for any kind of average value of anything. But then to find out the interesting things, your a sub n's, that's your cosine portion, right? That's equal to 2 over your time period, integral over any time period of f of t cosine n omega naught t dt. And similarly, your b sub n is equal to the exact same thing over here, just using sines. And everything else is the exact same. And then to convert it to the intuitive version, we can create your complex number, c sub n, which is equal to, the real part is your amount of cosine, and we'll subtract from that the amount of sine. And then we can represent that thing as having a magnitude and having an angle. And that magnitude is the same as our a sub n's, and that angle is the same thing as our phi sub n's. So if we want to have it in this sort of intuitive version, we'll first calculate our little a sub n's, little b sub n's, and then we will use this formula to convert it into our capital a sub n's and phi sub n's. And the last thing we just talked about at the very end of last class was the amplitude spectra. And the amplitude spectra is just a plot of a sub n versus omega sub n, where omega sub n is just that fundamental frequency times its harmonic for n equals 0, 1, 2, and so on. And this has a lot of intuition, right? If this is our plot of it, of our amplitude spectrum, maybe this is equal to 2, 4, 6, 8, 10. So maybe this is the amplitude spectrum for a particular periodic waveform. And this says, hey, this thing has got a fair amount of low frequency energy for omega of 4 or less, and it decays away pretty fast for higher values of omega. There's a lot of intuition here, right? This is loaded with intuition. If I told you that this is the the waveform of your EKG, of the waveform that shows how your heart is beating. And this is a perfectly good one with absolutely no other noise. But with a noisy signal, it's the same thing, but we're going to add this stuff, where this is the noise. Take a look how just ridiculously easy it is to say, well, I can fix all that by designing a filter. And my filter is going to pass values out here, and it's going to cut down, minus 40 dB per decade frequencies up here. Here's my low pass filter. I can find out exactly where its critical frequency is. It's at 10 radians per second. And I can even then figure out, if it drops down at minus 40 dB, how much it cuts down these different amounts. Because out here at then 100, it would cut it down by 40 dB, and I can see if it cuts down this noise sufficiently. And if that's not a sufficient amount of noise for me to cut it out, I'll keep increasing my filter order. What filter order is this? Ryan. I'm sorry, Aiden. What filter order is this particular one at minus 40 dB per decade?
Second order?
Yeah. And if this wasn't enough, I could make it be a sixth order or eighth order. All right. And you know how to just put these parameters into that filter designer. This would be a Butterworth low pass cutoff frequency of 10 radians per second, second order, and you could design that. Then we also talked about phase spectra. And that's the plot of phi sub n versus all this. And there's less intuition there. That's saying for a zero phase input signal, how much will that passed signal, after it goes through your filter, be shifted left or right?